Welcome viewers to another video from JD Productions. In today's video we're looking at Year 11 Physics, Area Study 2, how is energy from the nucleus utilised. The topic will be particles in the nucleus, and our skill will be to complete a sample hurdle task paper. So thanks for joining us, let's get straight into it. So this sample paper will be broken into 4 sections. The first section looks at nuclear stability and the fundamental forces. Consider the radioactive nuclei radon-212. So there we have our standard notation for radon-212. Question number 1 asks us to state the number of protons in the radon-212 nucleus. So here's the content that can be extracted from the traditional isotope symbols. So the number of protons is equal to the atomic number Z, shown above, which is number 86, as shown. So that question is worth 1 mark. Very simple, it's just the atomic number. Number 2, state the number of neutrons in the radon-212 nucleus. The number of neutrons is equal to the mass number A, take away the atomic number Z. So in this case, it's going to be 212, take away 86, giving us an answer of 126. And that's worth 1 mark. Question number 3, state the number of nucleons in the radon-212 nucleus. Now the word nucleons describes the number of particles inside the nucleus. It's the sum of both the neutrons and the protons. And it's simply given by the mass number A, which in this case is 212. Again, worth 1 mark. Question number 4. A second radioactive isotope of radon is radon-211. So here's our isotope of radon-211. Question 4 asks, complete the following statements by filling in the blank spaces. The first statement is, the isotope radon-212 and radon-211 have the same. We have to fill in the blank spaces. And the second statement, the isotope radon-212 and radon-211 have different. And again, we fill in the blank spaces. So first of all, radon-212 and radon-211 have the same atomic number and the number of protons. Okay, they both have 86 protons. That's the similarity. And the difference between radon-212 and radon-211 is they have a different mass number. 212 has, as the name suggests, a mass number of 212, and radon-211 has a mass number of 211. Because the number of protons are identical, it's actually the number of neutrons that is the difference. I suppose you could also have accepted a different number of nucleons. 1 mark for each. Question number 5, our final question from section 1. Complete the following fundamental force summary tables by filling in the gaps. So the nuclear particles experiencing the strong force are quarks and nucleons. Holds the nucleus together effectively. The role within the nucleus for the weak nuclear force is that it's used to cause beta decay. Effectively, it allows neutrons to convert to protons and protons to convert to neutrons via the changing of up and down quarks. In terms of attractive or repulsive forces for electromagnetic, both exist. Electromagnetic forces can generate repulsive and attractive forces. And finally, the effective range of gravity, well, it's infinite. Half marks for each of these 4 responses, a total of 2 marks. Section number 2 looks at nuclear half-life. Seaborgium-266 is a synthetic element that has a half-life of 30 seconds. Question 1. A sample of Seaborgium-266 has an original activity of 64, that is 64,000 decays per second. What would its activity be after 120 seconds? And we're asked to show full calculations. So first of all, we're after the amount. In this case, it's the activity in kilobecquerels. The original amount is 64 kilobecquerels. The half-life is stated as 30 seconds. And finally, we're asked what the activity would be after a time or a duration of 120 seconds. So step number 1, let's work out the number of half-lives. So the number of half-lives is equal to the total time divided by the time of one half-life. So that's 120 seconds divided by 30 seconds. 30 goes into the 120 4 times, so 120 seconds represents 4 half-lives of Seaborgium-266. Step number 2, let's now find the new activity. Here's our equation that allows us to forecast into the future, where A is the new activity that we're trying to calculate and A0 is the original activity. The n in this equation represents the number of half-lives. So let's sub those values in. It's 64 kilobecquerel multiplied by 1 over 2 to the power of 4, where the 4 is the number of half-lives. Now 2 to the power of 4 becomes 16. So it's 1/16 of 64 kilobecquerels. That gives me a value of 4 kilobecquerels. We'll give you 1 mark for finding the number of half-lives correctly, being 4, and the final mark for finding the new activity after 4 half-lives, that is 120 seconds, of 4 kilobecquerel. Question 2. A sample of Seaborgium-266 has an original mass of 200 grams. How many grams of the original 200 gram sample remains after 90 seconds? And we wish to show full calculations. So we're after an amount. In this case, it's the mass in grams. The original mass is 200 grams. The time for half-life is 30 seconds. And the duration of time we've been stated here is 90 seconds. So first of all, let's work out the number of half-lives we're dealing with. So the number of half-lives represents the time in total divided by the time of a single half-life. So 90 seconds divided by 30 represents 3 half-lives. Step number 2, let's find the new mass. So here's our equation, A equals A0 times 1 over 2 to the power of n, where A is the new mass in this example, A0 is the original mass, and n is the number of half-lives. Let's substitute our values in. The original mass was 200 grams, the number of half-lives was 3. 1 over 2 to the power of 3 becomes a fraction of 1/8, and 1/8 of 200 gives me a new mass after 90 seconds of 25 grams. 1 mark for the number of half-lives calculated to be 3, and 1 mark for the 25 gram as a final answer. Question 3, a sample of Cesium-266 contains 1.0 by 10 to the 10 nuclei. How many nuclei were present 60 seconds prior to this point in time? And we want to show full calculations. So yet again, we want to work out an amount. In this case, it's the number of nuclei. The original number of nuclei was 1.0 by 10 to the 10. The half-life, as we know, is 30 seconds. And the total time here is 60 seconds. So let's find the number of half-lives. So we know that 30 will divide into 60 exactly 2 times. So this represents a duration of 2 half-lives. Step number 2 is to find the new number of nuclei. Now, instead of going forward in time, whereby the number of nuclei will halve with every half-life, we're going back in time for 2 half-lives. So instead of dividing by 2 with every half-life, we're going to multiply by 2. So this equation is used when we're going back in time. A is the new amount of nuclei, A0 is the original amount of nuclei, and n is the number of half-lives going back in time. Let's substitute our values. 1.0 by 10 to the 10 is the original number of nuclei, and we're going to multiply that by 2 to the power of 2. The new number of nuclei is 4 times the original. It gives me a value of 4.0 by 10 to the 10 nuclei. 1 mark for the number of half-lives and 1 mark for finding the new number of nuclei. Our final question in this half-life section. The amount, that is percentage, of the radioisotope francium-225 is recorded over a 22-minute period, the results of which are displayed in the graph 1 below. Question number 4. Use graph 1 to determine the half-life of francium-225. So we can see that at a time of 0, we have logically 100% of our sample remaining. There's been no decay. If that 100% were reduced to 50%, being half of it has decayed, that would represent from our graph, if I move across and then sketch down, a time of 4 minutes. So again, at 0 minutes, I've got 100% of the sample remaining. At 4 minutes, I only have 50% of the sample remaining. So it took 4 minutes to reduce the sample remaining by 50%. Therefore, the half-life of francium-225 is 4 minutes. Section 3, types of radiation. The following is a full decay equation for thorium-234 undergoing beta minus decay. So we start with thorium-234. It decays a beta minus particle, 0 and -1, a high speed electron, and doing so it produces a protactinium-234 nuclei. In terms of energy conservation, there is also an antineutrino that's generated. So to do a full decay equation, we must use the correct symbols for all the nuclei and the particles, and we also must use the notation of the mass number and the atomic number. So you'd need to use your periodic table to construct the full decay equations for the following radioactive nuclei, and we're asked to provide the answer in the traditional nuclei format. So question number 1, polonium-189 undergoes alpha decay. So it's ejecting a 4,2 helium or alpha particle. And in doing so, the atomic number is reduced by 2, so it goes from 84 down to 82. And the mass number is reduced by 4, so it goes from 189 down to 185. We check element number 82 on the periodic table, and it is in fact lead. So you get 1 mark for correctly labeling the helium nuclei, the 4,2, and the second mark for correctly labeling the daughter nuclei, being lead 185. Question number 2, carbon-14 undergoes beta minus decay. Let's draw this equation. There's our beta minus. This is very much the same format as our example, so we can use that as a template. So when we undergo beta minus, we've got a -1 here. On the bottom, when we plus that with 7, that will get us back to 6. So our atomic numbers increase from 6 to 7, which means it's going to be nitrogen from the periodic table. And the mass number stays the same. It's 14 at the top of the carbon. There's a mass number of 0 for the high-speed electron, and the antineutrino has no mass number, so it's 14.7. And of course, you must state the antineutrino also to demonstrate a full decay equation. 1 mark for the beta minus particle, and 1 mark for both the nitrogen-14 and the antineutrino. Question number 3, potassium-37 undergoes beta plus decay. So here's our beta plus, it's a positron. It's got an atomic number of +1, so 19 when it ejects a positron actually drops down to 18. It goes 1 down in the periodic table, which when we check our periodic table is the element argon. The mass number, however, stays exactly the same. Okay, so the daughter nuclei for this decay is argon-37. It also ejects, obviously, a beta plus particle, which is a positron, and in doing so, it also ejects a neutrino to maintain energy balance. Now, all these 3 parts must be provided for full marks. The marking breakdown, 1 mark for the positron, and 1 mark for both the argon-37 and the neutrino. Our final decay equation, question number 4. Technetium-99 undergoes gamma decay. So here's our equation. As we know, gamma is not a particle. It is part of the electromagnetic spectrum, high energy, high frequency, and low wavelength. So this is its symbol. It's the Greek letter for gamma, and it's got a mass number of 0, an atomic number of 0. And accordingly, there is no change in the actual structure of our daughter product. The parent nuclei and the daughter nuclei are exactly the same. The only difference is this is now a stable arrangement, whereas this was an excited or an unstable arrangement. 1 mark for the gamma symbols, including the zeros, and 1 mark for the correct identification of technetium. Question number 5, complete the following radioactive decay summary table by filling in the gaps. The charge of an alpha particle is +2, it's got 2 protons, half a mark. The mass of an alpha particle, it's the heaviest of all the radiation forms have here. Beta plus, single positron, beta minus, single electron, and gamma has no mass at all, half a mark. When emission occurs for beta plus particles, it occurs for nuclides with too many neutrons. The process of beta plus decay converts a neutron into a proton and a high-speed positron that's ejected, half a mark. The ionizing power of a beta plus particle is medium, not as high as an alpha particle, but stronger than a gamma ray, half a mark. The speed of a beta minus particle, and also a beta plus particle for that matter, is approximately 90% the speed of light, half a mark. Finally, the penetrating power of a gamma ray is the greatest. It's a form of electromagnetic radiation, so it has great penetration. So that is a half mark. Our final section, section 4, radiation and the human body. So a series of questions centered around the following. James's brain has a mass of 1.4 kilograms. It receives 2.8 joules of energy via beta radiation. Here's a table looking at the various organs and the tissue weighting. Here's a second table looking at the different forms of radiation and the radiation weighting. So question number 1. Calculate the absorbed dose received by James's brain, and we're asked to show full calculations. So first of all, D is the absorbed dose, that's our question mark. M, the mass, is 1.4 kilograms, as stated in the question. And ER, which is the energy of the radiation, is 2.8 joules, also stated in the question. The equation for absorbed dose is as follows. It's D equals E over M. We substitute our values in, 2.8 joules divided by 1.4 kilograms, gives us the absorbed dose received by James's brain of 2 gray. 1 mark for the correct substitution into the correct equation, and 1 mark for the final answer of 2 gray. Question number 2, calculate the equivalent dose received by James's brain. Now, to calculate the equivalent dose, we have to look at the different forms of radiation and the radiation weighting. So we're talking about beta radiation, so the weighting of the radiation will be a 1 for beta. The equivalent dose has a symbol H to do with the health impact on the tissue. The original absorbed dose was 2 gray from our previous question number 1, and the weighting of the radiation is 1.0 for beta, as shown in the table highlighted green. Here's our equation to work out the equivalent dose. We substitute in our correct values, an absorbed dose of 2 gray and a radiation weighting of 1.0. Gives us an answer of 2 sieverts. 1 mark for correct substitution of values into the equation, and 1 mark for the correct answer of 2 sieverts. Question 3, calculate the effective dose received by James's brain. When looking at the effective dose and making this calculation, we have to consider the organ, that is the brain, and the weighting of the tissue, which is a value of 0.010. So let's perform this calculation. E is a symbol for effective dose, and that's our question mark. H we just calculated before, which was our equivalent dose of 2 sieverts. And in this case, the tissue weighting for the brain, as shown in the table, highlighted green, is 0.010. Here's our equation to work out the effective dose. We simply multiply the equivalent dose by the tissue weighting. So our equivalent dose was 2.0 sieverts, and our tissue weighting was 0.010. Multiply them together, and we get an effective dose for the brain of 0.02 of a sievert. It can also be written as 20 millisieverts. 1 mark for correct substitution of values into our equation, and 1 mark for the correct answer. Our final question, question 4. What short-term effects, if any, would be experienced by James? Now we need to support our answer with suitable dose figures. So an appropriate answer would be the absorbed dose, D, is 2 gray, which is between 1 and 3 gray. This indicates that immediate health risks, such as nausea or burns, may be experienced. 1 mark to describe the short-term effects, and 1 mark to reference the absorbed dose of 2 grays as a suitable dose figure. You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.